Hello everyone, this is Cameron Snow. I am one of the co-founders of Danomics.com and I am a geologist and petrophysicist by training. In this webinar, I'm going to be covering mineral inversion, why we should be using mineral inversions, and how to apply mineral inversions to the Danomics software. So, with respect to what we're going to cover, we're going to start off with why we use mineral inversions, and we're going to go into some of the theory behind it. Then we're going to cover how you set it up in the software, and then how I like to analyze and QC the results. So when you think about petrophysics, a lot of people think about this deterministic well flow where we, calculate clay volume, then a TOC, then a porosity, and then a saturation. This is the bedrock of petrophysical interpretations, and it's easy to understand because all the equations can be worked through step by step, in something like Excel or with a calculator. And this works quite well if the lithologies are relatively simple and our zones are relatively homogeneous. However, if this is not the case and we have complex lithologies and our zones are not homogeneous, we have mixed lithologies, then we need to add a layer of sophistication. Often we do this by using a mineral inversion. So the workflow is very similar, except instead of using something like a density porosity with a fixed matrix density, we'll use a mineral inversion where we will calculate the volumes of each mineral and then use those to calculate a grain density, which we will then use to calculate the porosity on a depth step by depth step basis. This reduces some of the issues associated with complex and variable lithologies, and I like to use it because it's quite stable across depositional systems. So like, for example, as you move from onshore to lower shore face to offshore, for example, your mineral mix isn't changing, and so you continue to get a good quality porosity in that type of a situation. So it can work quite well in a lot of those cases. Okay, so just a quick example to highlight why we want to do this, and where we can be led astray if we try just to use a parameter for a zone, a fixed parameter, instead of using a mineral inversion based grain density. So let's imagine we have a top and base of a zone, and within that zone we have a limestone, a sandstone, a calcite cemented sandstone. So if you wanted to evaluate the limestone, you would use a matrix density of 2.71. Then your porosity would be correct for the limestone, but it would be incorrect for the sandstone and the calcite cemented sandstone. You would be overestimating those to variable degrees. If you set it at 2.65, you're going to be correct for the sandstone, but then you're going to underestimate your porosity to varying degrees in the calcite cemented sandstone and in the limestone. And if you set it for the calcite cemented sandstone, then you're going to be wrong for the limestone and the uncemented sandstone. So what you would really want to do is you'd want to use a different matrix density for each of the lithologies. So you might be thinking, oh, fine, I can just pick another top here and another top here, and then I'll just set those extra parameters. Okay, you can do that, but then imagine if it was highly intercalated and you had limestone, sandstone, limestone, sandstone. You're not going to want to split it up that much. Or imagine this calcite cemented sandstone was variably cemented. Then you're going to have to use a different matrix density at every depth step. And so that's why we go from using a row matrix to a row grain density in this equation. Because that row grain density we're going to calculate at every depth step. And this allows us to perform our evaluation without subdividing at every lithological break. Okay, so let's look at a couple of examples. First example here, let's just look at that calcite cemented sandstone, and let's assume it's 65% quartz and 35% calcite. If we were analyzing this as a sandstone, we might give it a matrix density of 2.65, and if our log is reading 2.58, that means we calculate 4.2% porosity. However, if we're using a grain density, we're saying, okay, 65% quartz times 2.65, 35% calcite times 2.71. That gives me a grain density of 2.67, which means my porosity is actually a bit higher. It's 5.5%. So that's about a difference of a third. So, that's a pretty substantial, miscalculation in your volumes just from that small change. So especially important in these low porosity systems. So let's imagine another scenario where you have a combination of, you have an organic shell with kerogen, pyrite, calcite, quartz, and clay. So the first question is, what should your matrix density even be? How do you go about determining that? So let's say you set it at 2.75 because that's what you've been told the density of your shell is. Well, that means you're going to calculate 9.7% porosity. But then, if you take the grain density approach and you evaluate all of these components in their correct proportions, you get a much lower grain density, which means you get a much lower porosity in this case. So in one case, you were underestimating using the row matrix value. In the other case, you were overestimating. So, that is why it is so important to do a mineral inversion until you get that grain density correct at every depth step. So what is an inversion and how does it work? Basically, we have C times V equals L, where C is a matrix of our mineral properties, V is the volume of each component, and L is the log response. And if we think about this on a single log, let's say 3 mineral system, what you'll see is that if we know the density of quartz and the volume of quartz, and the density of calcite and the volume of calcite, and the density of dolomite and the volume of dolomite, and those were the only 3 minerals in our rock, we could tell you what the bulk density measurement of the log would be. And, same thing goes for PE. The PE value of quartz times the volume of quartz, PE value of calcite times volume of calcite, et cetera, et cetera. And that gives you your PE response. So, if we know all the mineral components and we know the volume of all the minerals, we can calculate what all the logs should be. Thus, we can rearrange all that so that if we know the mineral components and we know the log response, we can back solve for the mineral volume. So how do we do this? We just rearrange this equation. So now our mineral volumes is equal to the inverse of our properties times our log response. Okay, so now we know our logs and we know the composition, so we're going to solve for the volumes. And then once we know those volumes, there's a lot of interesting things we can do, like calculate the grain density. Okay, so that shouldn't be that hard to understand conceptually. It involves a bit of matrix math, but that should be something you can kind of reason through as long as you remember kind of that single curve example and just expand out on that. Okay, and just to visualize this, so here's a kind of a simple example. We have our components, so here's each of our minerals and here's the properties of those minerals. Here are the logs that correspond to those properties, so 2.64 and 2.71, 2.87, etc. Those are our density values. Minus 0.01, 0, 0.2. Those are our neutron values, etc. And so this inverted model that we're going to solve for, that's the volume. Okay, so now that we have that visualized, let's let's move along. So we've got a few concerns with mineral inversion, or you may have a few concerns. We rarely know all the minerals that are present in a rock, but we generally know all the major constituents. We don't know with perfect accuracy all the log response of all the minerals, but we generally know it well enough to get a pretty good prediction. And there are often way more minerals than there are logs, which means that we're often in an underdetermined state. That's fine. We can still solve the equations. It's just our answer may be a bit non-unique, especially with response to our mineral volumes, but often the grain density comes out the same. So it's kind of a wash there. So in practice, when we are solving for these volumes here, it's excruciatingly difficult to do by hand, and it would take you a prohibitively long amount of time. However, any kind of computer can solve this problem. However, sometimes it'll give you things like negative volumes. So when that's the case, we need to put constraints on the analysis. We need to say the volume of any mineral is going to be greater than 0 and less than 1. And once we've done that, we're not going to get a perfect answer anymore. So now we need to decide to minimize on some criteria. So we might say that, our actual log minus our predicted log, that gives us some value of incoherence. So let's minimize on that. Okay, but the logs are in different scales and they have different levels of uncertainty. So, now we need to calculate an incoherence that is weighted by some factor. And then we need to do that for all the logs. So we calculate a total incoherence. That's the difference, but the weighted difference between our actual and our predicted logs for each log in here, and that is, how we force this solver to give us the volumes. So that is the process here in a nutshell, and most vendors offer some sort of variation on this basic method, but I will say, it can vary with respect to what defaults that we all use. We're often close, but there's some details around the edge. We certainly use different uncertainties for the logs. There's a lot of different published values out there, so we may take one set and another vendor may take another. The way that we solve for this total incoherence, we all basically take the same approach, but there are some subtleties around whether or not you square these values or not. Once again, pretty similar, but some subtleties. And different companies also handle constraints a bit differently. And I can tell you that I know at least one major commercial package that is doing this in a way that we can show is mathematically inconsistent. And what I would say the biggest problem is in many cases, it's not been published, it's not explained in a lot of detail, or it's considered a trade secret. What I will say is that Doveton's Mathematical Petrophysics gives an excellent explanation of this process, and that is by and large what we follow. Where we vary substantially from that is that on the software side, we have used a very specific type of solver that allows us to generate results very quickly. So once we have the results, we know all the mineral components as well as the mineral volumes, and we can use that to calculate a grain density. So volume of mineral 1 times the density of mineral 1 plus volume of mineral 2 times the density of mineral 2, and so on and so on. And then we divide that by the sum of the volumes, and this, I should stress, is for the matrix or grain components only. So we're not including the water or hydrocarbon phases. This is just the solid components. And that's how we calculate our grain density. And then we also generate predicted curves that we can use both as a QC on our model and to use in other work if you would like to. So for example, we'll generate a predicted PE curve, that you may want to use in your correlation work, for example. And we can also get a porosity calculated directly from the inversion. That would just be the sum of all the fluid phases. So, number of things we get out of the inversion. So with respect to how we do inversions in Danomics, basically you go to the module drop-down menu here in the top center. You select inversion, and that will pull up the interface for that. When we look at this in detail, the first thing we need to do is set the mineral mix here. And I advise choosing what I would call a minimum viable mineral mix. So, if I'm looking at a sandstone, for example, I might choose quartz, calcite, clay, and then my hydrocarbon water phases. If I know there's no kerogen, I know there's no pyrite, I'm not going to add those because that'll just put me in a more underdetermined state. We can set the properties for each component as part of this as well. And we can customize this mineral mix as needed. So when you first pull it up, the zone will say default, and when you set this, that'll apply to every zone. But then you can go in and you can, set the mineral mix and the curves that are used on and the properties that are used on a zone by zone basis, just using this drop down menu there. So when it comes to modifying the mineral properties, first piece of advice, most minerals don't have a lot of variation in the properties. So don't go in and like start screwing around with them, right? Like the properties for quartz and calcite, dolomite and whatnot are, they're fairly constant. You're not going to see a lot of changes in those. Now, what does vary a lot are things like clay, and that's because we are using a generic clay. We're not using kaolinite or smectite. So, you can play around with the density, the neutron response, the P response, the clay resistivity, sonic value, etc. This is where you have the wiggle room in your interpretation. The water and hydrocarbon properties, these should be tuned to your area of interest. So, worth paying attention to here. For setting the curves, we've got the standard curves in here, density, neutron. We use U instead of PE. So U is just the product of density and the PE curve. Sonic conductivity is turned off by default, so you'd have to turn that back on. And the one thing you'll notice is that we don't use gamma ray. The gamma ray it varies too much among minerals to really be useful to us. And I will say that clay and kerogen are a bit of a special case. So we are using our deterministically derived at clay and kerogen, and we're putting those in as essentially constraints on the analysis. So once we have performed the inversion, let's say we're looking at our key well, what do we need to inspect? Well, I'd say inspect the mineral volumes results. Make sure that makes sense to you. Does that look right? Are you getting a bunch of dolomite when there's no dolomite, for example? Go in and adjust your mineral mix, etc. Inspect the grain density results. Do those look fairly good up and down the wellbore? And then look at the predicted curves. Do your predicted curves and your actual curves match? And if not, go in and iterate and make adjustments on on as needed basis. And then when you move out to doing this for multiple wells, start looking at these zone by zone maps of things like grain density, looking at average porosity maps, etc. When it comes to passing your inversion results into the porosity, you just go to this porosity method and you can select either min solver porosity or the strict min solver porosity. The difference is that the min solver porosity just takes out the grain density and uses that in a density porosity equation, so you still need to input your own row fluid here. The strict mineral solver porosity takes the sum of the water, oil, and gas phases and uses that in the inversion, or in the porosity, I should say. So that's how you pass that into the porosity to actually use the results. A few words of caution and troubleshooting. What's your curve suites? Do you have at least a triple combo? If you don't, you're going to have a very difficult time, successfully performing a inversion. The PE and or sonic curves, they are helpful, but they are not required. So I would say just pay attention to what happens when you have those curves versus not having them. The system will automatically handle that for you. So you don't need to worry about that, but you just need to worry about the impact of not having them on your results. If your grain density is too low, the first thing that I would check is to see if your TOC result has been miscalculated. A lot of times I notice up in the shallow hole, maybe people overestimate TOC and that throws off their grain density. Or they don't have any heavy minerals, so there's no dolomite, there's no pyrite. So the system may struggle to put in to calculate enough density. So Those are some things to check if the grain density is coming out too low. If the predicted curves aren't matching, first thing I like to do is go check the clay properties. If that's not the solution, then maybe you need to change your mineral mix. And one note on that is be careful for major changes in the mineralogy. So, for example, moving from the Delaware Basin to the Central Basin platform, you see some major changes in the mineral mix, and so, you need to go in and customize that. There are alternative methods that we have. So, for example, we have something called the Roma-Yuma porosity in Danomics, and essentially what this is you calculate a apparent matrix density and apparent matrix U value, and then you calculate a volume of quartz, dolomite, and calcite, and then once you have those, you add clay into the mix, and and then you can calculate a grain density from that. Now, the thing here is it means you have to have a PE curve. If you don't have a PE curve, result's going to be null, and that's probably the least common curve that I see in a lot of data sets. You can also do a kind of a poor man's grain density where you back calculate it, from a row matrix apparent, using a cross plot porosity. Now this, it's a bit incestuous, but it can be useful, especially if you don't have much control on the mineralogy, or if you've got some very sparse data sets. And this is called the quote grain density porosity in Danomics. So, in summary, your inversion, should not be a black box, solution. You should understand the inputs, and you should understand at least conceptually how this works on a single curve basis. And you need to understand why you're doing it. You're doing it so you can better cope with complex and mixed lithologies. And because of that, it provides a superior solution to porosity. And it's also quite stable over large areas when used carefully. So that's why we use a mineral inversion. If you have any questions or you need any help with it, feel free to contact me at csnow@danomics.com, and we can set up a screen share to get you taken care of. Thank you.